The year is 1982 and you've got a friend in the biz who hooks you up with a ticket to go see Comdex. And while there, you see some of the wildest, most epic computing hardware ever conceived. You are thoroughly in love and you have to get your hands on a mini computer. But you don't have the $40,000 it takes to buy something like this Centurion. However, since it's 1982, the TI-9900 here has been on sale for a little while, and it's getting so thoroughly trounced in the market that Texas Instruments has dropped its price tag all the way down to $100. So being the budding young hacker that you are, you run out, you buy a TI-99, you hold it proudly above your head and you say, "Behold, my first ever mini computer." And all of your friends who have Commodores laugh at you and call you all sorts of terrible names, saying that that is not a mini computer, that is a microcomputer and a home computer, and a terrible one at that. But little do they know that in the center of this TI-9900 beats the heart of a 16-bit mini computer. The year is 2025. Welcome back to the present. The whole point of this series is that I want to build a homebrew computer, and I've actually already built one homebrew computer. That's this thing on the wall here. This is the UE1, a 1-bit vacuum tube computer that I built over like the last 3 years from the ground up. And it's a functional computer. It'll calculate Fibonacci, it'll do math routines, it'll do conditional branching, and it's finished. I don't intend to go any further with this project than where it sits currently, which means it's time for the next homebrew computing project. And I do have a sequel for UE1 planned, UE2, and it's also going to be vacuum tube based and much, much more capable. But before we get into that, I do want to play around with a little bit of silicon, notably the TMS9900, which is the CPU in that TI-9900. But if you were kind of hoping to see me hold that TI-99 up at the beginning of this episode and then at the end of the episode have a completed, fully functioning homebrew mini computer, I'm sorry, that's not going to happen. This is the beginning of probably a quite long series of videos where I really want to do a deep dive into both the TMS9900 CPU and the difficulties of building a homebrew computer, even if you're using a CPU that already exists. What even is a homebrew computer? And this is one of those things where everybody's interpretation is going to be just a little bit different. In my personal opinion, a homebrew computer or homebrew CPU is something that is built by hand and requires creative effort. A prototype computer built by someone or a company for a commercial product is not a homebrew computer. Also, I don't think a kit computer, something like the RC2014, as awesome as I think that thing is, qualifies as a homebrew computer. That's a kit. So there are two homebrew computers that I am taking a massive amount of inspiration from. And the first is CommodoreZ's Cactus. And this is a 6502 based homebrew running at 1 megahertz with 32 kilobytes of static RAM, 2 kilobytes of non-volatile RAM, 16 kilobytes of ROM, has dual RS-232 capabilities, has 16-bit parallel I/O. It can produce 32 by 32 monochrome composite video. But what makes this one really, really special in my book is that it has a front panel that can do direct memory access. This is something that was incredibly common on mini computers like the Data General Nova or the Data 620, but you almost never see on homebrews. And I think CommodoreZ absolutely knocked it out of the park. It is a very, very cool homebrew. Now there's one more homebrew that I am just absolutely in love with, and this is TechAV's RAP 030. This is a Motorola 68030 CPU and a 68882 FPU running at 25 megahertz. It has 512 kilobytes of flash ROM on an 8-bit bus, has 16 megabytes of RAM on a single 72-pin SIM, has one Motorola 6850 serial port and 8 16550 compatible serial ports, has an IDE controller with support for 2 compact flash disks. This thing has real deal multi-user capability, and I have personally seen it running multi-user BASIC and Unix. A homebrew that's running Unix. This is like proper real deal mini computer level performance out of a homebrew. As a matter of fact, I would call TechAV's homebrew a mini computer. But this raises the question of what even is a mini computer? In the beginning, there were just computers, huge things like the IBM 1401 or Univacs that took up massive amounts of space and were the size of a New York City apartment. But as we marched on into the 1960s and 1970s, transistors gave way to integrated circuits, which allowed computers to become smaller. So small and medium-sized businesses could get their hands on something like this Centurion right here. It still packed a ton of power, but it was small enough to easily fit in a room. Therefore, this is dubbed a mini computer because it's much smaller than the computers of yesteryear. But as we marched on through the 1970s and into the 1980s, all of the discrete ICs that were used to build up the compute section of these machines were shrunk down onto a single chip, creating things like the 6502 or the Z80 or the TMS9900. And these were stuffed into very small machines that you could then put on your desk at home, plug into your TV, and use away. And these were called microcomputers. And so there it is, pretty cut and dry, relatively easy to understand. It's all done by size. So computers, mini computers, and microcomputers. We can pick that all out super easy, right? Well, not quite. This is a Data General Nova 1210, and this is the entire computer. The ADM3A data terminal sitting on top of it is just used for input-output with the user, and this Techtran tape drive next to it is our mass storage. But these three components is the entire package. So a Data General Nova is absolutely a mini computer, but this is not much bigger than an IBM PC. So it's not size-based, but the CPU in this thing is built out of discrete components. It's almost entirely 7400 series logic. So there must be our delimiter. A mini computer is something that uses discrete components for the CPU, right? And again, not quite. This is a heavily case modified PDP 1173, and ignoring the case modifications, which in this instance actually make it smaller and more compact, the PDP 11 can be seen right here on the front. This white ceramic chip here is the PDP 11 CPU. This is what they call an LSI 11, or a large scale integration PDP 11. Essentially, all of the discrete ICs that made up the CPU of older PDP 11s were shrunk down onto a single IC, which can be seen right here. So there you go. This is a microcomputer then, right? Man, I just can't call it a microcomputer. PDP 11s are mini computers. Not only that, I would call this particular PDP 11 a super mini because we have a massive vector processor bolted to the side of it. If this isn't a microcomputer and it is a full-fledged mini, then how come the TI-99 with its TMS9900 that is a scaled down version of the TI-990 mini computer CPU not also a mini computer? And the answer, I think, can be found by looking at the motherboard of the TI-99 4A here. And right in the center is our big, beautiful TMS9900. It's a full 16-bit processor that can run up to 3 megahertz. Interestingly, there's only 3 registers built into the CPU, a program counter, a workspace pointer, and a status register. all of the registers that the programmer is going to access are actually stored in RAM. And the workspace pointer points to the base address of 16 registers located in RAM. And by just updating the workspace pointer, you can switch from one group of registers to another incredibly quickly. And you can do that using full hardware interrupt support built into this CPU. So this is absolutely mini computer grade stuff hanging out in the middle of our home computer here. But if that's the case, why was the TI-99 considered to be quite slow? Well, it all comes down to memory access. Those CPU registers are hanging out in these two chips right here. These are fast static RAM. Because there's two of them, that gives us a 16-bit word that the CPU can access all at once. And there are 128 words in this memory. And it doesn't have to be CPU registers. You can store anything in this 128 words, but 128 words is quite limited. So the rest of the memory is all over here, which is dynamic RAM. Now, that's not the weird part. The weird part is that there's only 8 chips. Right above them, we have this big chip with a whole bunch of thermal compound on it. This is the TMS9900 video display processor. And these 8 chips down here create 16 kilobytes of memory. This is dedicated RAM for storing anything that has to do with putting an image on the TV, the screen, the colors, the sprites, and so on. But depending on what's being displayed, that's not going to use very much memory. So the rest of this 16K here is available for the CPU to use. So the reason the TI-99 struggled so much is because it just couldn't access memory rapidly. It had to wait for the VDP to become available, and then once the VDP was available, it had to wait yet again for it to retrieve 2 bytes from the slow DRAM and multiplex it onto the bus. It's a bit like having a Ferrari stuck in traffic in the middle of downtown Dallas. You're just using like 1% of its potential, but also it's completely out of its element. This CPU is all about heavy hardcore number crunching and multi-user capability, but it's stuffed into a machine that's all about single users and video display stuff, like playing video games. It's just completely out of its element. And so this brings us back around to, what is a mini computer? Well, I think a lot of people are going to disagree with everything that I'm about to say, but in my personal opinion, I feel like a mini computer is all about capability when compared to microcomputers of the same era. So a home microcomputer is all about displaying things on the TV. Maybe you have a single floppy disk and it's a single user. But a mini computer is all about heavy hardcore number crunching, lots of users, anywhere from 16 to 32 simultaneous users, and big, big storage. This Centurion behind me, with the way that it's spec'd out right now, has 100 megabytes of storage available in it. In 1981, 100 megabytes was pretty ridiculous, and this thing could be spec'd out with well more than that. And this was a low-grade machine. The TI-990s could have tons of storage. So that is our goal with this TMS9900 Homebrew mini computer. Multi-users and big storage. And in order to achieve that, we're gonna have to pull the CPU out of this motherboard here and throw the motherboard away. No, we're not gonna do that. I'm gonna put this motherboard back in the TI-99 and keep the TI-99 because I love the TI-99. And I just ordered some parts off of eBay that we have to build with. Every CPU needs a clock, and the TMS9900 is no exception. But it is a little weird in that it needs a 4-phase clock. So there is a dedicated chip, the TIM9904 here, that generates this 4-phase clock. But it gets even weirder in that it has to be a 4-phase 12-volt clock. And we should get phase 1, phase 2, phase 3, and phase 4 toggling just like they show in this graph here. So I've got a little breadboard here set up to test it, and I've essentially just wired that up exactly like they outline in the datasheet for the TIM9904 here. We have a quartz crystal, a little tank circuit, and then 4 20 ohm resistors that connect the 12 volt 4-phase clock over to the TMS9900 CPU here. But before we can plug the scope into this and check to see if our clock chip is working, we got to figure out the power supply here, because this chip requires plus 5 volts and plus 12 volts, and the TMS9900 requires plus 5, plus 12, and minus 5. And ultimately, we're gonna wanna run a UART for RS-232, which means that we're gonna need minus 12 as well for 4 total voltage rails. I'm a big fan of using what I got laying around, and this big chunk of plywood will work perfectly, I think. It's the perfect width for 4 of these Meanwell supplies to fit. Now I realize that 4 150 watt supplies is mega overkill here, especially for the negative 12 volt rail, which will maybe pull 1 watt in total. However, I think this gives us some room to grow in the future, because who knows what peripherals we'll try throwing at this thing. And ultimately, I'll probably tear these down and rebuild an era-appropriate supply in their place once we have an idea of where the build is going to end up. Once these are all tied down tight though, I'll start running the wiring to power everything up. All the AC inputs need to be tied in parallel, and I know my use of zip ties here is going to drive some of y'all mad, but this is just temporary until we get all the wires run, at which point I'll go back through and wire lace it. I'm also wiring in a power switch, though this is just one that I salvaged once upon a time. Finally, let's power it up and check the voltage levels. Looks like our negative 12 volt and negative 5 volts are looking good. Our plus 5 volt is a little high, I adjusted that later. And finally, the plus 12 volt looks good. All right, let's give our little breadboard a test here. I've been having trouble with my power switch back here, so I'm probably gonna have to change that out at some point in time. This was just a random one that I had salvaged out of something, so that's not surprising that it's fighting me. But let's see if we can get some oscillations going on here. I've got the scope set up. Oh, that time the power switch actually did seem to work. There we go. My breadboard does not make the best of connections, but check that out. We've got wibble wobbles going on. I'm zoomed way out. Let's see if we can get the trigger working a little better here. And yeah, there we go. Check that out. Let's take a single shot here. Yeah, look at that. There's our 4 phases of the clock. Phase 1, 2, 3, and 4 in yellow, green, blue, and red. And you can see they cycle absolutely perfectly. Look at that. That is excellent. Now we just need to put this design onto a PCB and give that a test. For the UE1, I used a piece of software called DesignSpark PCB to do all my layouts. I really like DesignSpark, but they've lately moved to an online-only model. I live out in the middle of nowhere, and sometimes the internet just goes out. But without internet access, I can't even view my files in DesignSpark. So I made the switch over to KiCad, and it's been difficult. The learning curve is steep, and the whole program feels less intuitive. But once I got the hang of it, it wasn't so bad. For the PCB layouts, I'm going to be limiting myself to boards that are 150 millimeters by 100 millimeters. This is because this is the rough size of a single-sided PCB that I really like from Paramount 3D. I'm using single-sided PCBs because I find it's actually faster to bend up jumper wires than it is to flip the board over, realign it, re-zero, and cut a second side of copper. I'm also using really fat traces here. My trace widths are 1 millimeter and my minimum trace separation is 2.54 millimeters, which is ludicrous by even 1960 standards, but this works really well with my production method. I'm going to be machining my PCBs on this Bridgeport EasyTrack with an Accurite mil-power CNC conversion. It's massive and a bit like using a rocket launcher to hammer in a nail, but once I got the settings dialed in, it's such a treat to use. My first step is dropping in a 2x4 and flattening it off as a sacrificial layer. Once it's good and flat, I stick double-sided carpet tape to it. Then I spray the non-copper side of the PCB with alcohol to get it clean before sticking it to the double-sided tape. The cutter that I'm going to use to cut my isolation tracks is a 1/8 inch shank 0.1 millimeter tip 60-degree V-bit.
At a cutting depth of 0.2 millimeters, this removes 0.331 millimeters of copper per pass, and we'll be doing 3 isolation passes. Once the bit is in the collet and tightened down, I'll slowly drop it until it's nearly touching the copper. Then I'll use a 0.04 millimeter feeler gauge to figure out when it's precisely at the surface of the copper. Once I'm happy, I just hit the datum button and tell it Z equals 0. Next, I'll move the bit over to the front left corner, as this is our origin point. I honestly just kind of eyeball this one, because we're going to do an edge cut later. Once it's close enough, it's back into datum and hitting X equals 0 and Y equals 0. Then I coat the entire surface of the copper with 30 weight oil. This helps keep the bit cool during cutting, but more importantly, it catches all the fine flecks of copper and fiberglass. Finally, I need to load the program up. And even though I'm loading from a CF card, the MillPower software calls it the floppy, which I find hilarious. It takes about a minute for a program this big to load up, which, as you can see, is 96,000 lines long. We're ready to fire and forget this thing, so let's turn the spindle on, press the go button, and we're off to the races. I usually watch the first few cuts to make sure something didn't go off the rails, and so far this is all looking good. It's churning through the steps of the program real fast and slicing out nice and pretty lines on the copper. At this point, it's good to go. I can walk in and go play Doom the Plutonia experiment or something. Now, I know some of y'all are gonna panic and yell at me about doing this in a well-ventilated area, and rest assured, the area is so well-ventilated, we're practically outside. That's why we have such insane problems with dirt daubers coming up the works. Plus, it's already chasing down 100 degrees or 39 Celsius outside here in Texas, which means it's chasing down 100 degrees in the shop. I didn't spend hardly any time watching this thing cut. That's what the GoPro time lapse is for. After the isolation cut is done, it's time for a tool change. But first, let's give this thing a bit of a clean. That looks awesome indeed. All right, let's get the V-bit out of the collet. And next, we're going to drill the through holes. For this, I'm going to use a 0.9 millimeter drill bit, which is tiny to say the least. To make sure the drill bit is properly zeroed out, I'll bring the spindle down until the bit contacts the board. Then I continue to bring the spindle down, pushing the bit into the collet. Once my Z-axis indicates 0 millimeters, I know the bit is at the right height, so I just fully tighten up the collet, locking it in place. Then we just load up the next program, which is much smaller this time, hit go, and we're off to the races yet again. And there are a lot of reasons I prefer to machine my PCBs instead of etch, but this is a major one. There are maybe 300 through holes on this particular board, and with the CNC here, I literally just hit go and walk away. It drills every single through hole absolutely perfectly every single time. This program finishes up much faster, and then all we need to do is just give it a quick vacuum, and we're in for our final tool change. I'll remove the drill bit, and the final tool we're going to use is this, a 1.5 millimeter end mill. We'll be using this to do the board outline cut. I'll use the same trick that we did with the drill bit to zero out the mill. Once the Z reads 0, just tighten down the collet, hit go, and walk away. I actually messed up my 0 point in the program, so ultimately I had to readjust my 0 point on the machine and run this program again, but that was an easy enough fix. The isolation cut took the longest amount of time, but from initial setup to completed PCB you see here took just 4 hours. I love machining boards because I can go from idea to fully populated PCB in a single day. It's absolutely brilliant. Now, sometimes there are little pieces that don't get sliced out in between the traces. Usually it's fine, but I must have had my 0 point off ever so slightly today because I have a few of these things left. 10 minutes with an X-Acto blade though, and everything cleans up really nicely. So let's solder this bad boy up. Like usual, start with the smallest components first. And in my case, that's going to be the jumper wires. Then I move up to resistors, capacitors, the IC socket, and finally all the pin headers. The last step is simply just dropping the IC into its socket, and man alive, that came out amazing.
And here's the finished product, and I'll admit that there appears to be a lot more going on than just the clock, which is just this tiny little piece up here. But all of this stuff down here is just future-proofing. Certain signals that go to or from the ROM, RAM, or CPU are going to need to be pulled up or pulled down. And so every single signal that's going to be moving along our card edge connector here comes up through these 4.7 k ohm resistors into this connector. And then from this connector, I can wire wrap to either plus 5 volts or ground, creating a pull up or pull down for whichever signal needs it. Now there's a couple signals that I know for sure absolutely need it, but I think most of these are probably going to remain empty. But because I have these headers here, I can tie things high or tie things low as I need them. And here we go, first proper test. We'll go ahead and flip the power switch on. And yeah, check that out. We are oscillating just like we should be. We'll go ahead and take a single shot of that. We can see all 4 phases of the clock perfectly. There's a little bit of noise on it, but that's probably because I don't have ground probes on these 3. I'm just kind of relying on the ground probe of the first one. But let's see if we can measure the frequency here. So let's do measurement. And yeah, 1.0666 megahertz. The Doomslayer is going to show up if we're not careful here. But there we go. That's how I built it. I wanted it to run at 1 megahertz, and it looks like it's going to be doing that perfectly. So there we go. We built a complete overkill power supply as well as our first circuit board for the TMS9900 Homebrew, and these two together are producing a beautiful 4-phase 12-volt 1 megahertz clock for the TMS9900. So all we need to do now is get this clock into that CPU and see what happens. And that's exactly what we're going to do in the next episode. We're going to get the CPU out, get it onto a circuit board exactly like this, plug both of these into a backplane, bolt that to this mess down here, run some wires to it, and flip the switch and start probing signals. It should be really exciting, and we're going to continue on building after that. We're going to add ROM, we're going to add RAM, we're going to add UARTs, and who knows, sky's the limit as long as it keeps going smoothly. So I know that today was a whole lot of talking, but I think it was good. It got us all kind of on the same page about what this project is, where it's headed, and why we're doing things the way we're doing them. So I hope you're as excited about this project as I am, because I think this is going to be a ton of fun. I want to thank you all so much for watching, and I hope to see you in the next one.